Hello, quick video on vectors and lines and their definitions in 2D and 3D. We can quite often have to find position of an intersection of two lines, or we might want to find the distance of a point from a line, and we might want to do that in 2D or 3D. And what I thought we'd do is start by going through the line equations in vector form for 2D and 3D and see how we can use those. Okay, let's start off. Well, what we've actually got usually, let's have a look, is we've got a point on a line. Here's our point P, and we can work out what the vector is to take us to that point P. There's our vector P. So in this case, our vector is the vector 2, 3. And then we start moving along our line here. So I could move from point P and I could go up the line, what we call the line vector. In this case, that is the line vector 2, 1. So I can start heading up and down this line depending on the multiples of the vector 2, 1 that I apply. And we use a parameter, so that's like our multiplier, here our 2, our multiple, to decide how far we want to go up our line. So when t equals 0, we're at the point P. When t equals 1, we've moved up to this point here, 4, 4. And if t equals 2, and then we're adding 2 lots of the vector 2, 1. So we end up here at 6, 5. So this is probably the easiest version of the line equation to use. So we've got our output vector, our xy, we've got our initial point on our line, and then we've got a multiple of our line vector. And that's written in this form here, that our output vector position, r, is our vector p plus t lots of a. Okay. We can find the intersection between two lines using this format. So here's our first line, that's the red line. And now let's pick a second line. This is going to be our yellow line. So this one's got it goes to the point 6, 2. That's this point here. There we are. And it's got a line vector which goes 1, 1, effectively 1 along, 1 down. Yep. And then we've got we've got a different parameter there for this one, for this line, yeah, because we effectively got two different parameters. There's our t parameter there and our u. You can have different values. So let's use this format to find the point of intersection here at x, y. Well, we need to find what the values of t and u are such that they are both satisfied, both equations are satisfied at this point x, y. And effectively what we're going to do is we're just going to equate x and equate y. So if we equate x from the red, the x value from the red line is going to be 2 plus 2 lots of t, and from the yellow line the x value is going to be 6 plus 1 lot of u. Therefore, we can rearrange that, can't we, to see that u equals 2t minus 4. And then we can look at the x value, so the y values, and for the red, our y value is 3 plus t times 1 from our a vector, and for our y value, so from our yellow line, our y value is 2 plus u times minus 1, and we can rearrange that equation there, these two here with a bit of cancellation. We end up with 1 plus t equals minus u. So here I've got two simultaneous equations in u. I'd recommend that in this sort of work you get into the habit of using substitution rather than trying to do elimination. So here I'm going to substitute in equation 1 into equation 2 in place of u. So there's in my bracket there for u is 2t minus 4 from equation 1. I've put that into 2. So I get 3t equals 3, and therefore t equals 1. Now if I want to find the point of intersection, I now know what my t value is, which I can substitute into the red line equation there. So let's do that. So I've got my value xy is going to be my position point 2, 3, a point on the line, plus our t is 1 here, so one lot of vector 2, 1, that's our line vector, and therefore our point of intersection is 3, 1. Sorry, 4, 4. My brain's going there, wasn't it? Okay. What else can we do with this format? We can also look at finding distances using this format here. So here's our red line again. I've got a point here at 0.15, and what I really want to do is to find how far away that is from my line, and the shortest distance from my line will be when this green line here, the vector between the two, the red line and the point, is at right angles. Yeah, it's perpendicular, and I'll start talking and using the word orthogonal a bit later on when we talk about 3 dimensions, but here we're in 2 dimensions. Well, we know that if these two vectors are at right angles, then I can start with my line vector, that's the one going in this direction here, and I can rotate it round to get that one there, and therefore my vector, line vector 2, 1, is going to become, here we go, is effectively going to become, isn't it, 1 minus 2. Yep. Can you see how we've effectively swapped those, the x and y's over, and we've changed the sign? So that's the equivalent of creating the negative reciprocal that we've done without vectors, isn't it? And therefore we've created a line here. There's our line in effect, this line here. That we could see that we've got, actually we could create a line here, goes through the 0.15, and it's got a line vector 1 minus 2 down the bottom. So therefore we've got a line there for our green line. That's the equation of it, goes through the 0.15, and there's a line vector of 1 and minus 2. And here now we can use, as we did before in the last part, we can solve simultaneous equations here for the xl and the y value, and we can therefore find our 2 simultaneous equations here in t and u. We can then substitute out for u as we did before with 2t plus 1, and we find that our minus 2 here and our minus 2 there cancel out, so in this case t equals 0. And if t equals 0, we can substitute t equals 0 into our red line, our main original line equation. There's our 0 going in there, and therefore we can see that the point of intersection is at 2, 3. Okay, let's go back and have a look at our diagram. Yeah, that looks right, doesn't it? That point there is clearly 2, 3. And once we know the position of the 2 points, we know we were starting at the 0.15 and we're going to the 0.23, where we can use Pythagoras in all these equations, can't we? In our distance between the 2 points, using Pythagoras, we can see the y distance is minus 2, the x distance is plus 1, put that into Pythag, and there we are, the hypotenuse here, d squared, the distance squared is 1 squared plus 2 squared, so d equals square root of 5. So that's how we can find distances in 2 dimensions. We can use exactly the same formats here for working in 3D. Yep. So rather than just having x and y now, we've got x, y and z. We've got our starting point. I've got one here, 2, 3, 1. And I've got a line vector here, 2, 1, 3. So the form of this equation is exactly the same, isn't it? And I would recommend that you work in this format. There is one other format you'll see in 3D in which we effectively get rid of our parameter t. So let's have a look and see how we can do that. If we look at the first line, our x line here, yeah, let's just go back to our line here. Our top line here is telling us that x equals 2 plus 2t, yeah. There's my x equals 2 plus 2t, and I can rearrange that to make t the subject, so t equals x minus 2 over 2. If I do the same thing with the y equation, here I got y equals 3 plus t, and therefore t equals y minus 3 over 1, and z equals 1 plus 3t, and therefore t equals z minus 1 over 3. And of course, as these are all t, then they must all be equal. And this is a sort of Cartesian form of a line equation in 3D. So therefore, x minus 2 over 2 equals t, which equals y minus 3 over 1, which equals y minus 1 over 3. And therefore, we get to this general form in this form here, where all of these values match the parameters x minus our x value, our point we know it goes through, divided by the x component of our line vector, and we do the same thing for y and the same thing for z. So there's three formats. There's a second format that people may show you in line vectors. There's a nice little summary. We can define a line in two different ways, either in this form here, which is the most useful, in the vector form. So I've got our x, y, z vector there. I've got a point vector that I know it goes through, and then I've got some multiple of the line vector. That's the one that goes along the line. Yeah. There's this other form here, Cartesian form of that, where we basically eliminating our parameter. And finally, if we want to know the distance from a line, well, we need to find the perpendicular to the line, perpendicular vector, which we can find easily by taking our line vector and flipping it around. And later on, when we look at scalar product, we could look at when the scalar product will be 0, and that will be in the next video. So there you are. Quick start off with line vectors and their formats.